there is a formula with which we can calculate the degree of unsaturation for any molecular formula. I'm going to show you this formula. It's not going to make a whole lot of sense at first, but as we start to go through some examples, I'll explain what this formula means. So our formula for degrees of unsaturation, the formula for index of hydrogen deficiency, is the theoretical maximum number of hydrogens, given the number of carbons, minus the corrected actual number of hydrogens, all divided by 2. So what does that all mean? What is the theoretical maximum number of hydrogens? Theoretical maximum number of hydrogens is just like we did up here. It's the maximum number of hydrogens that those carbons could have if the molecule was completely saturated. And again, that's just the 2n plus 2 formula for a given number of carbons. What does corrected actual number of hydrogens mean? I'll actually explain that as we go through some examples. And then we divide by 2 because every 2 hydrogens is 1 unit of unsaturation. So again, this best works. We can explain this best by doing a series of examples. So if we start with our 5-carbon hydrocarbon again, we'll bring that one back. And we draw in all the hydrogens. The molecular formula for this molecule is C5H12. If I were to go through this formula and calculate the index of hydrogen deficiency for this molecule, I would say that it would be the theoretical maximum number of hydrogens. For 5 carbons, that would be 2 times 5 plus 2, minus the corrected actual number of hydrogens. Again, I haven't really explained what that is, but for a regular alkane, we don't correct the actual number of hydrogens. The actual number of hydrogens is the actual number of hydrogens, which would be 12, and then I divide by 2. 2 times 5 plus 2 is 12, minus 12 is 0, divided by 2 is 0. The index of hydrogen deficiency for this molecule is 0. But I knew that anyway. There's no pi bonds, there's no rings in this molecule, so I knew that this one is, that there's no degrees of unsaturation in this molecule. But let's look at a different example. If I instead take this 5-carbon hydrocarbon and I add a bromine to carbon number 2, how does this change the degrees of unsaturation? Well, again, I can look at this molecule. I can see that there's no rings and no pi bonds, so I can see that the index of hydrogen deficiency should be 0. But let's go through our calculation and see how this changes. If we look at the index of hydrogen deficiency calculation for this molecule, we would say the theoretical maximum number of hydrogens, again, there's 5 carbons, so that would be 2 times 5 plus 2, minus the corrected actual number of hydrogens. How many hydrogens does this molecule actually have? Go ahead and count them for a second. Calculate how many hydrogens this molecule has. This molecule's molecular formula would be C5H11Br. So this molecule has 11 hydrogens. If I were to put 11 here and then divide by 2, I would get 12 minus 11 is 1 over 2 is 1/2. You can't have a half a degree of unsaturation. You can't have a fractional index of hydrogen deficiency. If you go through your formula and you end up with a fraction, that means you've done something wrong in your calculation and you should go back and check your work. That's why we need to correct the actual number of hydrogens. I know what the answer should be. The answer should be 0. This molecule has no pi bonds and rings, but if I just use 11 hydrogens, then I get a 1/2 as my answer, and that can't be. So I need to correct the actual number of hydrogens to account for the fact that this bromine is here. If we think of it in a thought experiment again, if I were to substitute this hydrogen for the bromine, I would have to get rid of this hydrogen to make room for the bromine. The bromine is taking the place of a hydrogen. This molecule is artificially 1 hydrogen deficient because we had to make room for the bromine. It didn't add any degrees of unsaturation, but we are artificially 1 hydrogen short because we needed a valence for the bromine. So to correct for that, we just do the opposite. Because this bromine is causing us to be artificially 1 hydrogen deficient, we take the actual number of hydrogens and we correct for it by adding in 1 hydrogen for every halogen in the molecule. Whether it's a bromine or a chlorine or whatever, in order to introduce that halogen in the molecule, we had to remove 1 hydrogen, which makes us artificially deficient in our hydrogen count. And so we just correct for that by adding 1 hydrogen. Let's start a little table over here, our correction table. If I have a halogen in the molecule, I correct for that by adding 1 hydrogen back in, because that bromine, that halogen, is taking the place of 1 of the hydrogens. If I then go through this calculation, 2 times 5 plus 2 is 12, 11 plus 1 is 12, 12 minus 12 is 0, over 2 is 0, which I knew anyway. But this is now, we can start to understand what I mean by correcting the actual number of hydrogens. Let's do another example. If I keep this same molecule with the bromine, and now I add an alcohol here, how does this change my index of hydrogen deficiency calculation? what correction factor am I going to need for an oxygen in the molecule? If we look at our IHD calculation, it would be the theoretical maximum number of hydrogens. We still have 5 carbons, so it's still 2 times 5 plus 2. Corrected actual number of hydrogens. What is the molecular formula for this molecule? Take a second. What is the molecular formula for this molecule? Molecular formula for this molecule is C5H11, H12, excuse me. No, yeah, H11. Yeah, H11. C5H11BRO. So when I go to calculate the corrected actual number of hydrogens for this molecule, what do? We start with 11, and then we correct for the bromine. Again, for the bromine took a place of a hydrogen, so we have to add one back in. But look what happens with this oxygen. Yes, we had to remove one of the hydrogens to make room for the oxygen, but notice oxygen brought along one of its hydrogen friends. It brought along a hydrogen, and we had to remove a hydrogen, so the net impact that bringing the oxygen along in this molecule is really 0. We had to get rid of the hydrogen to make room for the oxygen, but because oxygen has 2 valences, it brought along a hydrogen, and so there was no net change in the number of hydrogens in the molecule. So if I have an oxygen in the molecule, I don't correct for it, because oxygen has 2 valences, it brings along a hydrogen friend of its own, and so we don't end up correcting for it. So we had 11, we add 1 for the bromine, and we don't do any correction for the oxygen, and we divide by 2. 2 times 5 plus 2 is 12. 11 plus 1 plus 0 is 12. 12 minus 12 is 0 over 2 equals 0. Again, which I knew anyway. I know what the structure looks like. I can count the number of pi bonds and rings and see that the index of hydrogen deficiency needs to be 0 for this molecule. Now let's do one last example to finish out our discussion here. Again, we've got our bromine, our oxygen, and now we have a nitrogen in the molecule. What correction factor are we going to need for a nitrogen in the molecule? Take a second on your own, see if you can figure out how we're going to correct for a nitrogen given what we've talked about with the bromine and the oxygen. So if we do our IHD calculation, we'll start with the theoretical maximum. Again, we still have 5 carbons, so it's still 2 times 5 plus 2. Corrected actual, we need the actual molecular formula here. So the actual molecular formula is C5H12BRON. So our actual number of hydrogens is 12. The bromine, we were artificially short 1, so we had to bring 1 back in. The oxygen is no net change. We took the place of 1, but it brought along 1, so we don't have to correct for the oxygen. How about the nitrogen? For the nitrogen, we had to remove 1 hydrogen to make room for the nitrogen, but nitrogen brings along 2 of its friends. So we took away 1 to make room for the nitrogen, but it brought along 2 of its friends. Now we're artificially 1 hydrogen inflated in our hydrogen count. This nitrogen causes us to have 1 more hydrogen than we really should have. So to correct for a nitrogen, we are going to need to subtract 1 from our total in order to correct for that nitrogen. So we'll subtract 1 from the total here and divide by 2. 2 times 5 plus 2 is 12. 12 plus 1 minus 1 is 12. 12 minus 12 over 2 is 0. The index of hydrogen deficiency for this molecule is 0. Again, which we knew anyway. No pi bonds, no rings. We knew what the answer should be. This is how we correct for halogens, oxygens, and nitrogens in these molecules. If there are any other elements, I'm not going to list them all here, but you can go through the same thought experiment. What did it do to the overall hydrogen count, and how do I correct for that in my formula? So we'll do one final example. Let's say that we have some molecule with a formula C8H7NOCl2. What a ridiculous structure. Why would anybody make a structure like that? Whatever, doesn't matter. Let's calculate the degrees of unsaturation for this molecule. Our index of hydrogen deficiency calculation, we have a theoretical maximum, that's 2 times 8 plus 2, minus our corrected actual number of hydrogens. We actually have 7. The nitrogen caused us to be 1 inflated, so we need to subtract 1. The oxygen had no net change. The chlorine caused us to be 1 deflated, so we need to add it back, and there are 2 of them, so we need to add 2 back to that count and divide by 2. 2 times 8 plus 2 is 18. 7 minus 1 plus 2 is 8. 18 minus 8 over 2 is 5. There are 5 degrees of unsaturation in whatever this molecule is. That's a lot of degrees of unsaturation. I mean, we're looking at the ways that we can have degrees of unsaturation. 5 is kind of a lot. So much so that there's actually a trick here. Whenever we have 4 or more units of unsaturation in a molecule, that almost always means that there's some kind of benzene ring in the molecule. We look at the structure of a benzene ring, A benzene ring is a very compact structure that has 3 pi bonds and is a ring. Each of the pi bonds is a unit of unsaturation. The ring is a unit of unsaturation. So a pi bond itself has 4 degrees of unsaturation. So anytime we calculate our formula and we get a number 4 or greater, that almost always means there's a benzene ring somewhere in the molecule. It really probably doesn't mean we have a chain of 4 alkenes in the molecule. That's a little ridiculous. It's almost always a benzene ring. So if you see an IHD of 4 or greater, always start with the assumption that there's a benzene, unless there's some evidence that there's no benzene. This is an overview of index of hydrogen deficiency and how we calculate our index of hydrogen deficiency formula.